It is a real honor to be here. I was really excited when Alain Philippe reached out, I think last year, reminding me that I was an alum of the College of Humanities and that he was here to really kind of take a new approach to how the College of Humanities operates and how it reaches out to the community and how it communicates the benefits of a humanities education. And I hope you'll see as we go through the presentation today, it's kind of a hodgepodge of all the things that I have been involved with, for better or for worse. And kind of just following that creative human spirit. That's kind of the theme that I think runs through my career, my activities, and how I try to live my life. So it's kind of an autobiographical presentation, but I grew up here in Arizona. None of my family members had been to college before, didn't really know what college was or what opportunities awaited for you there. But I grew up in the desert. I was kind of like I call a desert rat kid. I scrabbled around in the arroyos and I got to learn all the cactuses, was really in love with nature and exploration. And I really, really wanted to be an explorer. That was kind of, when I was a kid, I wanted to go somewhere nobody had ever been before, set foot someplace nobody had ever been. And then, as you start to realize that there's very few places on Earth that you can actually do that anymore, but there's lots and lots of places in outer space. And I like this one here. I know it's not a great picture, but hopefully you recognize C-3PO and Obi-Wan Kenobi exploring the desert planet of Tatooine. So that was some early inspiration for me. I think I was 7 years old when Star Wars came out, and it was the greatest experience of my life at the time. I think as many people of that era can attest to. But I did end up at the University of Arizona. I was very fortunate. I did well in high school, and I believe there's still a program like this in place, but we didn't have any money, so going to an expensive college wasn't really an option for me, but I did well, graduated in the top 10 of my high school class, and because of that, there was a Regents presidential tuition scholarship that I was eligible for. So it really allowed me to come here and to understand what college was about. And I was really clueless when I look back on that. I had become independent. My mom was raising 3 kids. I was the oldest one. Me and my friends did a lot of backpacking. That was kind of one of our favorite things to do. I grew up on the northern edge of Phoenix. You could actually pack up your backpack and hike out of my mom's door, and within an hour or so be in the wild desert, which is now all housing developments. But back then it was kind of wild terrain. So I figured out how to apply to college. I got accepted here. I forgot to apply for housing. So when it came time to go to Tucson, I packed up my backpack and I hitched a ride with a buddy who was heading down this way. And my mom was like, "Hey, where are you going?" I said, I'm heading out to college. She's like, "Do you need a ride?" I was like, "No, I think I got it figured out." I was able to sleep on the floor of some friends' houses until I found a place to live. So that, I was kind of really self-sufficient. I don't have a lot of photos from this time, but I think these 3 kind of capture a lot of kind of what my college was about. So this one's one of my favorites. So AP mentioned that I was an American cultural counselor to students coming from Japan to study English for a couple of months here. And that was a great job. First of all, the students were just wonderful, very warm people that we made lifelong friendships with. And my job was to show them what life was like as a U of A college student in the late 1980s and early 1990s. So it was a pretty good time to be here at the U of A. So they made this shirt for me. Those of you who speak Japanese recognize this is kind of my name. You have to bend the rule a little bit, but that actually does say Dante. And it means warm hand, which they thought the warm kanji was particularly applicable to our relationship and to my personality at the time. So they thought that was really great. One of the other things I did was own a 72 Volkswagen bus and showing them American cultural life. We packed up and hit the road to go tour with the Grateful Dead during the summers, which was kind of the thing to do back then. It was a wonderful era if you're a Deadhead. Some of my favorite shows come from that period of time. So we really became great friends and went on great adventures all around the American West. Did lots of camping, lots of hiking, backpacking, that kind of thing. I was also studying math and physics. I actually started out in theoretical math. I didn't really know what I wanted to do. And at the time I was kind of exploring my own mind, human consciousness, the limits of human knowledge. I dabbled with philosophy, was very quickly talked out of majoring in that just for practical reasons. But theoretical math seemed kind of like on the boundary between you could go get a job afterwards and you could also do some really crazy exploration of how the human mind works. And then I slowly migrated over to physics because I wanted to understand, well, the fun thing about theoretical math is that you can develop logical constructs entirely contained within the human mind that have no application to the physical universe. And I thought that's just fascinating that you can do that. But you can also, of course, create all kinds of constructs that very, very accurately describe how the universe works. And that's the language of science, is mathematics. And so I always looked at my study of math as the study of a language. And if you want to describe very precisely how the universe operates, then mathematics is the language that's required to do that. So I moved into physics and started to learn how you actually speak the language of science by applying that math degree. But I also had a requirement to take a foreign language. That was kind of the general education requirement. 4 semesters of a foreign language was required. And this was in the 80s, and we thought Japan was going to rule the world. They were buying all the real estate in Manhattan. The Japanese corporations were big, and the economy was booming. And I wanted a challenge, for one thing. I wanted to understand how another culture that's very different than my background and my knowledge and my experience, how they thought, how they communicated, how they spoke. I was really intrigued by the kanji system and how they use pictograms to build up words and concepts. I still am, although I wish I had more time to study and refresh my skills. And so I took Japanese. I took a first semester Japanese to see what it was like. It was a 5-credit class. It was very intense. Really enjoyed it. Made a good friend who I know AP has reached out to, who also studied Japanese, and we challenged each other and spoke to each other. We were both in that counselor program, so we got a lot of experience speaking Japanese on a day-to-day basis, at parties or out to dinner or just hanging out, studying or whatever. And so I took my 4 semesters. By the time I was done with that, I had 20 credits built up in Japanese, and then I had other credits, like you had to take a non-Western civilization, so I took history of Japan. And you had to take a gender-focused study, so I took women in East Asia. And then I ended up going for a 3rd year of Japanese. So by the time I had all of those, I was up to like 32 credits in Japanese. I was like, geez, I only need 4 more credits to get a degree in this thing. So let me stick around. I took kanji writing for 3 credits. And I can't remember what the last one was, but there was one more course that came in and allowed me to complete the Japanese degree along with the math and physics double major in the College of Science. And so I graduated with that wonderful aspect of talent and skills in 1993. There's my mom. The one thing I have to say about this picture that I'll never forget this morning, because my mom showed up for the graduation ceremony, and we're getting ready to go. And I didn't know how to wear a necktie at the time, so I had to have help tying that around. And then she's like, "Where's your cap and gown?" And I went and I grabbed it, and the gown was still in the package from the bookstore. And she's like, "You didn't iron it?" And I was like, "What?" She's like, "Yeah, it's going to be all wrinkled." And sure enough, when I look at this photo, all I see now are the wrinkles in the gown, because I didn't iron it. I didn't even think about ironing my gown before the graduation ceremony. So we ran out the door because we were running late as usual. And then we took this picture, which is very prophetic, because right here, I had no idea what I was going to do. I decided I wanted to study planetary science, and in fact, I was going to go to Washington University to work on a spacecraft called Mars Observer, which was ultimately lost in space. But right there is an iron meteorite, and sure enough, that would come to define my future career. I really became interested in meteorites and the study of the origin of our solar system, and this rock is 4.5 billion years old, and it dates from the dawn of our planetary system. So that combination of studies really opened up a lot of amazing opportunities. So I mentioned I didn't know what I wanted to do. I was studying things because I was passionate and curious, but I wasn't kind of defining a career track at the time. And in 1992, kind of my summer of love, I lived in this van for 3 months and toured around the West, lived at Lake Tahoe for a couple of months and hiked and camped and got a job cooking breakfast at a local cafe there to keep some money flowing. And so when I came back for my final year of college, 92, 93, I got a job at a local restaurant. If those of you who've been in Tucson a long time may remember Mike's Place in Main Gate Square. kind of where the Marriott is now. They knocked it down a while ago, but it was a real dive cafe, famous for nickel pints of Old Milwaukee and 25-cent pitchers, just to give you a sense of what their specials were. And I was the breakfast cook. They had a 99-cent breakfast special, 2 eggs, toast, and potatoes. And I worked Saturday and Sunday morning, so I had to be in at like 5 a.m., and I would cook thousands and thousands of those breakfasts to the people who were out the night before partying, which I couldn't do because I had to get up at 5 a.m. and go to work to pay for school. And then in the fall of 1992, this job ad showed up in the Arizona Daily Wildcat. And it said, if you want to expand your universe and get paid, do we have a job for you? And that just blew my mind that there were jobs like that out there. And in fact, the Lunar and Planetary Laboratory, where I now work, was the one who sponsored that program. So I applied, and they looked at my background, math, physics, Japanese, and they said, well, what kind of project should we assign this kid? And sure enough, they put me on to a project called the Search for Extraterrestrial Intelligence. And so what the challenge they gave me was, they said, well, you're kind of a linguist, and we're looking for signs of alien intelligence in the universe. What are we going to say if we find them? Right? How are we going to communicate to them? What are we going to do with that? So my job was to sit there and think about, okay, you detect radio emissions from a civilization. And now you've got to answer them or alert them that, hey, we hear you, we're here, you're there, let's talk. And so, there's been attempts to do that. This is the famous Pioneer 10 plaque that kind of tried to show us what, humans are like and where we are in our solar system. And this is actually a roadmap to the Earth relative to a bunch of pulsars in the Milky Way galaxy. So if you knew what was going on here. And then the thing that I looked at here that kind of got me started on the idea was this is a hydrogen atom here. And I was like, hydrogen, that's the most abundant chemical element in the universe. It makes like 95% of the universe is the baryonic matter of the universe is hydrogen. I said, if you could communicate the concept of hydrogen, that's the basis for a foundation for a language to start talking to this other intelligence. Because if they're looking at the universe, that's what they're seeing, right? That's all around us. That's what makes up the sun. That's what makes up most of Jupiter and Saturn. So when you're studying the universe, you're studying hydrogen atom. And I applied the concept of mathematical set theory, where the interesting thing that quantum physics tells you is that the energy levels of the hydrogen atom are very specific energies. And that's how we study it around the universe. You look for electrons that are transitioning. It's what quantum physics tells you about. So I built a whole language system that started out just repeating the energy levels of the hydrogen atom and then getting a response from them saying, yes, we understand that. And then you could build up the whole periodic table from there. And then you've got all the chemical elements in the universe, and you can start telling them about what you're made out of, what your planet's made out of, and all that kind of stuff. So it was, the really takeaway message was that somebody paid me to sit there and think about how to talk to aliens. And I was like, man, that is the coolest job in the world. I said, I want a job like that. And sure enough, they said, well, you're not going to go get a career in SETI because it was kind of fringe science at the time. But it got me thinking about the origin of the solar system, the origin of life, the distribution of life in the universe, kind of the big questions that we ask ourselves as humans. Are we alone in the universe? Where did we come from? And where are we going? What does our future hold for us? So I got my PhD in planetary science. I studied meteorites and the chemistry of meteorites, very, very focused study about how sulfur got into the Earth, and it was a great study. And then I came here in 2001, and for the first decade, I was a chemist, studying cosmochemistry. And this will come back later in the presentation, I think, in a very fun way. So I created a laboratory group called the 9 Circles. Remembering this was 2001, so Pluto was still a planet back then. And so we had 9 planets in our solar system at the time. And those of you who are literature buff also know, what do you know 9 circles from? From Dante's Inferno and Purgatorio and Paradiso, right? There's 9 circles of hell. And so I thought that was a pretty cool way to kind of capture both the planetary science and the more humanity aspect of what I'm doing. So the group grew. I attracted students and staff members. Here's 6 of us to 2011, where there's almost 20 of us working together on these great problems. And I really enjoy working with the younger students, and still do. It's one of my favorite parts of the job, talking to them, opening their minds to the possibilities, career possibilities, and these big questions that we ask ourselves, and really enabling and encouraging them to pursue these kinds of careers. The person who hired me, and I apologize, this is a very difficult slide for me, Mike was my mentor. He was the director of the Lunar and Planetary Laboratory when I was hired, and in 2004, so I've only been here like 3 years into an assistant professorship where you're trying to build laboratories and get grants funded and develop your courses and recruit graduate students and do all the things that professors are expected to do. Mike calls me up and he says, hey, I've got a representative from Lockheed Martin Corporation in my office, and we're talking about proposing an asteroid sample return mission to NASA. And I was like, wow, that's cool. I was like, so what's up? He's like, well, I want you to come and join me, and I want you to be the deputy principal investigator for this program. And I was like, wow, that's a big responsibility. I said, what am I going to be? What am I going to do? What do you want? He says, it's going to be an easy job for you. He said, all you have to worry about is the science. Why do we want to do this? What are we going to do? What kind of asteroid do we want to go to? What kind of sample do we want to get? What are we going to do with that sample when it's back on Earth? And I was like, okay, that sounds pretty easy, because I know exactly where I want to go, and I know exactly what I want to get, and I know exactly why I want to get it. So I could do that in a couple of months. Give me some summer salary, I'll write the science program, and you and Lockheed Martin deal with the engineering, and you deal with the management, and the cost, and the budget, and the politics, and the administration, and all the other stuff you got to worry about to run a NASA mission like that. So that was 2004. We submitted a proposal that's humorous in hindsight to go back and look at it, because it's very naive. So we got NASA, when they grade your proposals, they give you 4 categories. Category 1 is, we love it, it's great, we want to fund it, it's high priority. Category 2 says it's interesting, it's not our top priority, but it still looks good. Category 3 means the science looks really good, but you have some technical problems in technology development that you probably need to go off and do. And category 4 is, you're rejected and we don't tell you why, just go away. And that's what we got. We got category 4 the first time. And so we're like, okay, well, are we going to do this again, or is that, and Mike's like, no, the team is good, the science is good, the concept is sound. He said the problem was the engineering was poorly written, and I was like, isn't that what we brought Lockheed Martin in to do? And it's like, actually, it turns out that if you're going to be the principal investigator, you got to understand the engineering side of this too. So we went back in. The next year, the opportunity came around again, and I decided I can't just focus on the science. I can't be stovepiped and just look at that aspect of the mission. I've got to understand, and I've got to communicate my science to the engineer who's trying to design the device that's going to actually make it happen. And we didn't do that the first time around. We kind of wrote the science section and then kind of wrote the engineering section, and that really showed up when you go back and read it. There was no common language across those disciplines. So I was very fortunate. I made a friend, the system engineer at Lockheed Martin. My wife calls him the brother from another mother. We were really, really tight and bonded, and we said, we're going to make this proposal sing, man. So we locked ourselves in the hotel room when we were traveling, and we just wrote, and he read my science section, and I read his engineering section, and we rewrote those until I could understand what the engineering said, and he could understand what the science section said, and it was one common line of thought between the entire process. We also brought the Goddard Space Flight Center in because we had problems with the management and budget, and that's what they were supposed to do. So we submit the proposal, we make it to the final round. So NASA down selects and picks 3 missions, gives you some money to go off and do a concept study report. I compare it to making the championship game in the NCAA basketball tournament. So we were like, all right, we're in. We're going up against MIT and a lunar gravity field mapper, and we're going up against the University of Colorado and Venus orbiter. And that's kind of how NASA picks these things. So we do a lot of work. At 2007, we submit that concept study report, and it comes back and it says, your science is great, your engineering is great, but your management section is terrible and your costs are unbelievable. And I was like, God, dang it, all right, so we're going to go in again, 3rd time. And I said, okay, I got the science, I got the engineering, now I have to learn how you manage and how you budget and how you control a budget and a schedule for a program like this. And that's exactly what we did. I took over the management and the science sections, and so by the end of the 3rd proposal, the science, the engineering, and the management were all the same language, all the same thoughts, and they were all connected and cross-referenced to each other. And we made Phase A again. We went through another concept study report. This is the document that we submitted, so that's about a 1,000-page binder. That's Volume 1. By the way, volume 2 was just as big, so we submitted a 2,000-page concept study report to NASA, and they loved it. It was, obviously they selected us. This was May of 2011. We got the word that we were selected, and then we're going to go and build and fly this thing. So that was really exciting. And then Mike had been struggling, and he passed away in September of that year. So I had to become the principal investigator at that point and take over the whole thing. So I miss this old guy, and I thank him a lot. And what we do is in his honor as we move forward. And again, I'm sorry for that. So we spent the next 5 years designing, building, testing, and getting the team ready to launch and operate the OSIRIS-REx asteroid sample return mission. And this is the awesome acronym that defines our program. That's my fault, by the way. I came up with all that. So every letter of the mission name spells out part of the science investigation. And what really drives us is this origin science, going back to those big questions that I first thought about as an undergraduate here at U of A. Where did we come from? And this asteroid, it tells part of that story. It's ancient. It's 4.5 billion years old. And we believe it's loaded with organic compounds and water molecules. And we think something like this brought those materials to the very early Earth and is the reason we have oceans and the reason we have life on this planet. So the idea is you go back and you understand the chemistry that led to us being here today on this beautiful, wonderful planet that we live on. And that'll help you understand how common is that process, how complicated was the chemistry, and how likely is that to have happened somewhere else in our solar system. And we actually think there's a couple locations in our solar system where there might be at least primitive life. And then, of course, elsewhere in the galaxy and elsewhere in the universe, ultimately getting me back someday to that SETI investigation that I was discouraged from pursuing as an undergraduate. We care about how we use telescopes to study asteroids. We care about mining asteroids. We care about asteroids crashing into the Earth and causing another extinction event like the dinosaurs experienced. And so when I told you that story, the first 2 times we wrote the proposal, we were the OSIRIS mission. And then we actually got to go into a higher budget program called the New Frontiers program. And so we wanted to keep the OSIRIS brand name because NASA knew who we were and what OSIRIS was, but we also wanted to indicate we were kind of bigger and stronger and better than OSIRIS. So we were thinking, okay, what should the mission name be? We should change it to reflect the New Frontiers class mission. And one of the team members threw out the idea, OSIRIS-REx. And we all laughed, like, AP is right now. And then I was like, that's actually pretty cool. I said, we're going to make that happen. So I call this my backronym. I made the words Regolith Explorer to fit the Rex part of the mission so that we could be OSIRIS-REx and be this awesome, cool NASA mission that we are today. So just so we're all on the same page here, here's a quick cartoon of our solar system. Not to scale, but the sun dominates the mass of the solar system. The planets have all the angular momentum of the solar system. In the inner solar system, you've got things made out of mostly rock and metal. Earth obviously has the liquid oceans. Out here, you have things made out of gases. Out here, you have things that are mostly made out of ices. And in between Mars and Jupiter, you have this belt of asteroids. And these look a lot like these planets in their composition, but as you go to the outer edge of the asteroid belt, they look more like the icy objects. So you have a compositional gradient out here. And we would say we really want to get out to the asteroid belt, get a sample of those carbon-rich asteroids, which are close to Jupiter, and bring it back to the Earth. But that wasn't really technically feasible, just because it would take decades to fly a mission like that. The good news is Jupiter prevented these things from forming a planet, which is why they're kind of frozen geologic remnants from the dawn of the solar system. And it's still stirring the pot up there. It's still causing trouble. It's still occasionally causing these asteroids to crash into each other, create a whole series of fragments, some of which come tumbling in to the inner solar system and create a transient population of near-Earth asteroids. Once something gets on an orbit like this, it's only going to survive for about 10 million years against the 4.5 billion year life scale of the universe. Most of the time, it's going to fall into the sun, but about half the time or less, it's going to crash into one of these planets, which is one of the reasons that we're interested in understanding these guys. So this kind of gives us a natural target. You leave the Earth, you find one that looks very much in an orbit like our planet, you spend some time there, and then it's easy, relatively speaking, to get back to the Earth from there. So we picked a near-Earth asteroid as our target. And then we set off to build this awesome, awesome machine. And these are just some of my favorite pictures. This one here is the very, very earliest stages. This is the core cylinder of the spacecraft here. Here you can see us dropping in the fuel tank, loading up our antenna, installing the polycam. This is one of the instruments we built here at the University of Arizona. And then the sample acquisition mechanism, which is kind of like a space vacuum cleaner that's going to grab the sample and bring it back to Earth for us. One of the coolest things that we did that really captured humanity's excitement and made people feel like they're part of the mission was we did this special microchip called the Messages to Bennu. And so here you could either put your name on the chip, you could put your cat's name if you wanted to. You could send a prediction about the future. We did an asteroid time capsule, so the sample comes back in 2023. And we said, send us a tweet of what you think the world will be, what will be happening in the world when we open up the capsule in September of 2023. And we picked like the top 100 predictions. So when we open up the sample return capsule, we'll release the 100 tweets about what people predicted. I think this was in 2013 when we ran that campaign. And then we also did art, poetry, music, whatever you wanted to, digital media. We included it on the chip and we put it onto the spacecraft. And so there's a copy on the OSIRIS-REx spacecraft, which will stay in space forever. And then there's a copy in the sample return capsule, which will come back to the Earth. So this was one of the things we did to really engage with the public, to make them feel like this was their mission, that they were part of it. And by far, these are the most popular images that we put out there. Whenever we mention the chip, the Messages to Bennu chip, we get thousands of likes on Facebook and retweets. And I mean, everybody just loves to feel like, my name is on the spacecraft and I'm part of the mission, or my cat's name is on the spacecraft and she's part of the mission. And so people just really, really resonated with that. So here's the spacecraft in September last year at Kennedy Space Center right before launch. So remember, I got that phone call from Mike in 2004. This is 2016, so a nice long journey to get us to the launch pad. And I never get tired of watching this video, so I'm going to get out of here. That's our Atlas V rocket. So that's September 7th when we rolled out to the launch pad. The spacecraft is in the nose cone right there. I lived in Florida for 3 months as we did the final assembly of the rocket and processing the spacecraft. It was really great. And since it was summer, I actually brought the kids for it. We got to live in Cape Canaveral Beach.
Status check to proceed with terminal count. Atlas systems, propulsion. Go. Hydraulics. Go. Pneumatics. Go. LO2. Go. Vehicle system engineer. Go. Anomaly chief. AC is go. Range coordinator.
I'm sitting right there.
LD is go. And permission for launch. Proceeding with the count. Status check. Go elements. Go Centaur. Call OSIRIS-REx.
5, 4, 3, 2, 1. Liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid vector and back.
There goes the spacecraft. It's really hard to describe the feeling that day. 12 years of your career sitting on a giant pile of explosives. and everything has to go exactly according to plan. And it really, the only word that I can describe it was transcendental. I felt like I was on that rocket, and I went into outer space that day. And I still feel like that. I still feel like when we see that spacecraft, when we hear from the spacecraft or see the images, that it's us, it's our spirit that's out there. So here's what we've done since then. We left the Earth. We've been in orbit around the sun. Here's the asteroid Bennu. It looks like we're catching up to it, but actually it's on a different plane than we are. It's below us at this point. And so just last month, on September 22nd, we did this maneuver we called our Earth Gravity Assist, where we timed it to within 1 second. Our flyby of the Earth flew underneath Antarctica, used the gravity of our planet to change the plane that the spacecraft was orbiting on to match that of the asteroid. And then that set us up for a rendezvous, which we will see Bennu starting in August of next year. So this just shows you what's about. We're about right there right now. And so in August, we get our first view of the asteroid, and then in November, we'll be in the proximity of Bennu, and the real adventure will begin, which is right about there. Okay, so during the Earth Gravity Assist, we were able to use our science instruments, including those awesome cameras that we built at the University of Arizona, to get some pictures of our home world. Here, this was right after we flew under Antarctica. We immediately turned around and started collecting data. This is the color images from our map cam. It's actually 3 images, one in red, one in green, one in blue filters, and then we stack them together to get this awesome picture. I really love this view of our planet because it's not one that people look at very often. And I always try to imagine that if you were an alien and you sent a space probe to view the Earth and you just did a flyby and you took this picture, you would really have no idea that there were humans living on this and that there was actually land. I mean, you see a little bit of Australia down here, and you see Asia over here, and then actually there is Baja, and right there is Tucson, Arizona. So if you were in Tucson on September 22nd, 2017, then you are in this picture. And here we got a shot of the moon, also a view that very, very few people ever see, because this is the near side of the moon here. The Earth would be over here in this field of view. And so you're used to seeing those mare, the man in the moon kind of things. This is the far side of the moon. The moon's tidally locked, so it's always got the same side facing the Earth. So you never get to see this side unless you send a spacecraft over there to take a picture of it. And then also the equator is down here, and this is the North Pole, so you can actually tell that we did that inclination plane change, and we're looking down on the moon from our normal point of view here. We were also, I talked about looking for life on the Earth, so we had a 4th filter that was the infrared filter on the camera. So here's the color image, and then it's going to fade back to that infrared image, which we mapped onto the green channel here, and this is what's called the Vegetation Index. So now you can actually see that there might be some life on this planet. So when you look at it in the visible, it mostly looks like an ocean world, a ball of rock covered in water. But one of the coolest things is here. Anybody know what that is? That's Hawaii. The Hawaiian Islands really pop out. You can see New Zealand. You can see the coast of Australia. You can see the jungles of Southeast Asia and the jungles of Mexico over here too. So very different view of our planet when you change wavelengths and look at it in the infrared. So here's what the timeline looks like. We launched, we just did our Earth Gravity Assist, and then the approach maneuver is in October, a little less than 1 year from now. We'll begin asteroid operations in November of 2018, and we actually can't leave until March of 2021 because we've got to wait for those orbits to line up again. And then it's a 2.5-year cruise home with the samples back on Earth in September of 2023, about 19.5 years after that first call from Mike in 2004, and then we get another 2 years of money to analyze the sample and actually do all the science that I was asked to write up in 2004. So here's just a quick view of what we'll do at the asteroid. So we get there, we start doing some flybys to get a good look at it. I like this view because it kind of gives you a sense of scale. The asteroid's about 500 meters in diameter, about 1,800 feet, kind of like the size of Push Ridge. It's about the size of our asteroid, and the spacecraft's about the size of an SUV. So we're going to spend a couple of years mapping this object. We're going to then find areas that look interesting where we think we want to collect the sample and do high-resolution characterization of those. And then ultimately tentatively July of 2020, we will actually send the spacecraft down to make contact with the asteroid surface. We will deploy this TAG-SAM device, which I mentioned it was like a vacuum cleaner. If you know how your vacuum cleaner works, it creates a low pressure area inside that pulls the air in. There's no air in at the asteroid, it's in vacuum. So we bring our own air, that's what these things are. These are bottles full of nitrogen gas. And when we touch the surface of the asteroid, we'll open one of those up. It's like a vacuum cleaner working in reverse. Will create high pressure underneath this head, which is basically an air filter. I would say it would look really at home on the carburetor of a 57 Chevy. Basically what it does. So we push that into the gravel on the surface of the asteroid. We open up the gas bottle. It fires the gas, which then expands up through a little valve and then is collected in a chamber on the outer edges of that device. That's going to take about 5 to 10 seconds. So we're going to contact the asteroid for between 5 and 10 seconds. Once we are confident we have a sample, then we will open up our sample return capsule. And we will put that entire filter into the capsule. And then we have some bolts that we separate here. We leave that behind. The capsule closes up. The entire spacecraft comes back to the Earth. But we spin up, and this is the only part of the vehicle that actually makes it back down to the surface. We'll hit the top of the atmosphere about 28,000 miles an hour. Most of that energy will be dissipated by the heat shield. We're targeting the Utah Test and Training Range just to the southwest of Salt Lake City. Once the capsule gets into free fall, we open up the parachutes. It's actually all done autonomously by the avionics on board. And then we'll go out there and recover this. Here's some footage from a similar capsule that was flown on a NASA mission called Stardust that brought comet dust particles back. And so we'll be, fortunately, in the morning when we collect these, they were there at 2 in the morning, and then the whole thing gets transferred to the Johnson Space Center in Houston, to the same facility where the Apollo moon rocks are today. And then we open it up and see what we got and start to unravel the history of our solar system. So that's my day job. As AP mentioned, I'm into really sharing that adventure, the excitement of what we're doing, and I get involved in all kinds of crazy things. Let me see, what do we got here? Right, so one of the things we did was put this movie together called Bennu's Journey, where we brought in artists to try to capture the story that we think Bennu records.
Rising and setting over billions of worlds, including our own. In this vast expanse, how did our sun, the Earth, and the planets come to be? In recent decades, our understanding of the solar system's evolution has greatly improved, but deep questions remain. To answer those questions, astronomers are preparing to visit someplace very small. Asteroid Bennu. A lump of rock and organic material, the early building blocks of the solar system, of Earth, of us. Bennu is a time capsule, and its journey takes us way, way back, 4.5 billion years. The raw ingredients of Bennu and our solar system originated in a stellar nursery, a vast cloud of hydrogen, helium, and dust. Our own sun doesn't yet exist. Nearby are hot stars like this one, quickly burning up its fuel and destroying itself in a colossal explosion called a supernova. The explosion destabilizes our cloud, causing it to collapse. In the geologic blink of an eye, 100,000 years, gravity and angular momentum flatten the cloud into a swirling disk. In the center, where molecules crash together tightest, a protostar revs up to incredible pressures and temperatures. Deep within the disk, clumps of dust not much larger than a grain of wheat are flash heated into droplets of molten rock, called chondrules. The source of this heat remains a mystery. Chondrules are destined to become the building blocks of the solar system. Coaxed by gravity and turbulence, the chondrules clump. They grow into the first asteroids, into mountains, into planets. The asteroids are rubble piles of rock, metal, ice, and organics. This large asteroid is the parent body of Bennu, a protoplanet whose size we can only guess. Closer to the protostar, a planet begins to form, and then dawn in the solar system. The protostar undergoes fusion and ignites, revealing our sun. But the solar system is far from finished. Jupiter most likely forms near its outer edge, but just 500 million years after the sun ignites, some believe that it slowly moves inward. Its massive gravity ripples the asteroid belt, disrupting countless asteroids and comets, flinging them toward the sun. They rain down on the inner planets, hammering and remelting large portions of their crust. Did these impacts also deliver organics and water, key ingredients for life? Back in the asteroid belt, Bennu's parent body is lucky. It survives this period of heavy bombardment. The solar system cools and calms. Jupiter and its many moons assume the orbits that we see today. Billions of years of quiet follow, more or less. Then a billion years ago, one theory suggests a collision shatters the protoplanet. Some of the debris loosely coalesces into a new, smaller body, Bennu. But Bennu will not stay in place. Dull, non-reflective, it slowly migrates toward the sun. Solar heating turns its warm side into a low-intensity thruster. Through millions of years, Bennu's orbit gradually tightens until it interacts with Saturn's gravity, altering its trajectory and hurling it into the inner solar system. Close encounters with Earth and Venus follow. Their gravitational tugs may have repeatedly stretched and reformed Bennu, turning it inside out and pulling off loose material. As a result, it has no satellites of its own, until now. Today, NASA is sending a spacecraft called OSIRIS-REx to explore Bennu and retrieve a sample. Why? Bennu has survived its long journey and settled into a near-Earth orbit, bringing its secrets within our reach. Now it is ready to teach us more about the solar system's history, its formation, its evolution, and our own place among the stars.
So that was really fun to kind of take all of our science. Everything in there has a scientific hypothesis. I have a blog that I write that I went through the science behind how we did it. Some of the other things that I've done to kind of get people excited is we threw a festival at the Fox Theater back in 2015. We called the Bennu Ball. And this was a variety show. It was cool. I was kind of the producer. I went out and got sponsorships to put it all together. So I gave a kind of a comedy story called Asteroid Friday, which maybe for a subject for another lecture. We had Flam Chen acrobatics. We had Chamber Lab doing experimental music. We had Tucson Improv doing comedy. Jeff Notkin, famous meteorite hunter, telling stories of his adventures. I would love to do another one like this if anybody is interested or has ideas. It was a really cool, fun way to bring the community of Tucson together, which is something I think is really important to do. We work with the College of Fine Arts. If you know where our building is, we're on 6th Avenue in Drockman, where our operations center is. And Professor Quiros and his mural painting class came out. I gave him a lecture about the mission. And then they put this 60-foot by 20-foot mural that they designed and painted on the side of our building, which kind of captures the mythology of Osiris as well as the science and the journey of OSIRIS-REx. And then, amazingly to me, my Japanese education came back to be incredibly practical and useful because the Japanese government and their space agency, they're probably the most ambitious group out there, and they're definitely the highest risk takers when it comes to planetary exploration, which I love. And so became good friends with the scientists. They have their own asteroid sample return mission that's flying right now. In fact, we'll get to their asteroid next year, so there's a lot of similarities between what they're doing and what we're doing. I love the Japanese kawaii culture. So you can see here, the rocket is launching the Hayabusa 2 spacecraft on its journey to their asteroid Ryugu, which is named after the dragon that lives at the bottom of the sea in Japanese mythology. And then when President Hart found out about this, she got really excited, and we actually invited the leaders of the Japanese Space Agency to come visit the University of Arizona and talk about ways that we could work together. And then we did a reciprocal visit where President Hart and a couple of the Arizona Board of Regents members, along with the director of the Lunar Planetary Lab and Stewart Observatory and the vice president for research, we all went to their headquarters in Sagamihara, and we signed a strategic partnership agreement between the University of Arizona and the Japanese Space Agency. And we are working together now very collaboratively to discuss ways to help each other, to explore the solar system together. We have a very tight coupling now between the OSIRIS-REx and the Hayabusa 2 teams, where we're sharing lessons learned, we share software, data analysis techniques, personnel. We have one of our postdocs is over there living in Japan, co-located for a year, and then we'll come back to Tucson, and we're inviting Japanese scientists to spend time in Arizona. So having that humanities education where I learned not only the language, but the culture, the history. When you go to Japan as a gaijin, you're treated a certain way, very politely, but also somewhat distant, until you can become part of the in-group. And then it depends on the social situation. And probably the most important thing that I learned is that when you go to a formal meeting and you're sitting around a conference table, you're not going to make a lot of progress in coming together with mutual agreement or finding out even what's going on or what they're worried about. But when you go out afterwards and you sit around and you drink sake and you eat the wonderful Japanese food, then things loosen up and you get to be more friends. And that's the relationship that it established. And what was interesting to me is NASA and JAXA work together on a lot of different projects, but there's always cultural miscommunications and problems. And I think we're helping to kind of bridge that gap here. So I never, ever dreamed when I was in college here that I would actually have a career where I'm exploring the solar system and studying meteorites and asteroids and speaking Japanese and working with colleagues in Japan. And it really shows the global appeal of space exploration. It's a good news in a world that needs some good news. And it's a unifying vision. People, scientists and explorers and engineers, they all get it. Your friends, your colleagues, your conspirators together in this journey to make something happen. So it's been a really wonderful experience and a relationship that I expect will continue to grow. And in fact, this is Masaki Fujimoto, who leads the Solar System Exploration Division at JAXA. Him and his team will be out here in a couple of weeks for now an annual planetary exploration symposium where we look at the new mission concepts that JAXA is developing and help them, give them feedback, reviews. We're also teaching them, one of the things that they've had a hard time with is when we go to a review, a technical review for OSIRIS-REx, we get hammered. We come out bloody, right? The review team is there to tear you apart, to prevent you from making mistakes. And the Japanese Space Agency had a lot of big, high-profile mistakes in their program, where they've lost spacecraft that they shouldn't have. And so we're teaching them that it's okay to criticize the design or the concept because you're trying to make it better. It's not a hostile situation. It's actually quite friendly, but it doesn't feel like it. When you're up there and you're getting battered but at the end you come out stronger and your missions come out better and your risk posture is greatly reduced. So something I'm very proud of. I do a lot of work with the community, especially in addition to the Alumni of the Year for College of Humanities. I was a Boys and Girls Club kid when I was little, and I'll show you a little bit of that. And I was inducted into their Alumni Hall of Fame this year. I do a lot of work with the Boys and Girls Clubs of Tucson, just about to join their board of directors to try to bring OSIRIS-REx and fund science into their clubs here and across the nation. And I was working with the national organization in Atlanta as well. And so I mentioned I was just inducted into the Alumni Hall of Fame. This has been a really great way to reach out to other people in other disciplines. I don't know if you recognize any of the other inductees here. This is Triple H from the WWE Wrestling Federation. This is Dr. Shine, who is on the board of directors for the International Space Station. This is Jason Witten of the Dallas Cowboys. Anthony Anderson, an actor in the TV sitcom Blackish. Tony Clark, former Arizona Diamondbacks player. And Skylar Diggins, who's a WNBA player for the Dallas franchise. So just to show you how we are getting out into the culture, I've got this clip from the induction ceremony.
Look at every walk of life and the people that the club touches, it truly is an amazing thing, and you have to look no further than here tonight. And this amazing group of people that I had the honor of sharing this stage with, and you know, you look down this list, and Dr. Dante Lauretta, just a cosmochemist. Did anybody else here on the way here have to Google cosmochemist to see if it was an actual thing? I did. I'm not ashamed to say I Googled it because I thought, look, that's something that the WWE might make up as a moniker for somebody. I could see us doing that, like, you know, please welcome the cosmochemist, Dante Lauretta! You put that followed up with some heavy bass rap music or something like that, he comes strutting down. It's money. I'm telling you. But it's legit. Cosmochemist.
Too legit, right? So I'm a little disappointed with the intro that I got here. I'm taking some cues from Triple H. Okay, so one of the other things I'm involved with is asteroid mining. I think this is the future. I'm really excited. I'm an advisor and on the scientific advisory board for a company called Planetary Resources, who is getting very serious about developing an economy in space, going out to asteroids like Bennu, particularly looking at the water. Seems like the water is something like Bennu. We anticipate holds about $5 trillion worth of water, which you can break up into hydrogen and oxygen and use for rocket fuel. So just another activity that I'm involved with, and looking forward to helping these folks get into outer space and really make it serious about human exploration of the solar system and becoming an interplanetary species. And then finally, AP mentioned I do develop board games. We just released our second game called Constellations, which is all about learning the patterns of the stars in the night sky and learning how they all fit together to create the view of the universe that we see from Earth. And then Extranaut came out last year, and it's about building rockets and going places. And you can, a lot of my personal experiences in here. You can fly Earth gravity assist to achieve a Bennu sample return mission. So it's really there to get kids excited about space exploration, to teach them something while they're having fun. And this actually did really well. We were named the best family board game of 2016 by Good Housekeeping magazine last year. So it's getting some traction out there, and it's been a really great way to share the adventure with a whole new generation of explorers. So that's just a quick snapshot of what's going on. I hope you see the value of my humanities education. There was a reason I was drawn to the college as a college student, and I really feel it expanded my worldview. It resonated with the kinds of things that I was thinking and wanting to do with my career, and it's a real honor to be the Alumni of the Year from the College of Humanities. I thank AP and all the colleagues over there. And I think it's just the beginning of a great relationship. We've got lots of plots and plans. He's a partner in crime over here to talk about how we take this amazing adventure that is OSIRIS-REx and the broader space exploration of activities that the University of Arizona is famous for, and really bring humanities perspective into that endeavor. So thank you for your time, and thank you for your attention, and thank you again for this honor.